Hi there, and welcome to this series called The Introduction to Electronics. Although electricity has been around since the beginning of time, the electrical revolution only really started at the beginning of the 19th century with men like Michael Faraday and Thomas Edison. These men helped us to generate, harness, and use electricity in ways that benefit humankind. Based on their discoveries, more and more scientists became interested in exploring the ways in which different materials are affected by electricity. The results of these experiments have led us into a new age, the age of electronics. Electronics is a branch of the physics topic electricity, and it looks specifically at the flow of charge through various materials. Scientists have found that different materials respond differently to the flow of charge through them. They have used this knowledge to make parts or components for electrical circuits that will affect the flow of charge through the circuit in various ways. Circuits which include these components are called electronic circuits, and devices which have electronic circuits are called electronic devices. They are usually able to work with small electric currents, making them cost and energy efficient. You can find electronic devices all over the world. The electronic age has affected the lives of almost all people on Earth, even those living in quite remote rural villages. Of course, electronics has also helped us travel beyond the boundaries of the Earth and explore our universe. In this series, we are going to investigate some of the ways in which different materials are affected differently by electricity. We will then see how these differences allow us to classify materials into three groups: electrical conductors, electrical insulators, and semiconductors. We will also see how these different groups of materials are used to make different electronic components. And we will examine some examples of electrical components such as resistors, capacitors, and diodes, including the light-emitting diode, or LED, in more detail. In today's lesson, we will focus on the group of materials we call conductors. We are going to start by revisiting a very important electrical investigation in which we see how current and potential difference change in a conductor. The experiment was originally conducted by George Ohm and is the basis of Ohm's law. We will then see if electrical conductors made from different materials all behave in the same way, and use a model called energy band theory to explain our macroscopic observations in terms of what is happening microscopically. By the end of this lesson, you should be able to state Ohm's law, draw conclusions about the resistance of conductors from experimental data, and use energy band theory to explain what happens when an electric current passes through a conductor. Before we get started on our investigations, I want to remind you about some important terms we use when investigating electricity. You should remember that electricity is the flow of electrical charge through a material, called an electrical conductor. We use the term electric current to describe the amount of charge passing through a conductor in a certain time. The size of an electric current, I, is measured using an ammeter that is always connected in series. Remember that the SI unit for measuring electric current is the ampere. There are two very important conditions that are required before an electric current will pass through any material. Can you remember what these are? Well, firstly, you need a closed circuit. If there is a gap or break in a circuit, shown here where the switch is open, no charge can flow through the circuit. When the gap is closed by closing the switch, the circuit is complete and charge can flow. Remember, we define the direction of electric current as conventional current. Conventional current is the flow of positive charge from the positive terminal of a battery around the circuit to the negative terminal of the battery. However, a closed circuit alone is not enough to ensure that current will pass around a circuit. The second important condition required before an electric current will pass through any material is a source of electrical energy. This energy can be stored in batteries or generated by moving a magnet through a coil. When a battery is connected into a circuit, we say that an EMF or potential difference has been applied across the ends of the circuit. A voltmeter can be used to measure this potential difference, V, by connecting two connecting leads across any 2 points in a circuit. We say that this way of connecting a voltmeter is a parallel connection. Remember, the SI unit of potential difference is a volt. Now, let's review what George Ohm found when he investigated the relationship between the current passing through a conductor, I, and the potential difference, V, measured across the ends of a conductor. He showed that the potential difference is directly proportional to the current passing through the conductor when the temperature is kept constant. The gradient of the straight line graph is a ratio of potential difference to current and is called the resistance of the conductor. Today, we measure the resistance of conductors in ohms in honor of George Ohm. You should know that metals conduct electricity and are classified as electrical conductors. This means that metals should obey Ohm's law. But do all metals behave in exactly the same way? Why don't we join Tate in the lab for some experiments and find out?
Hi everybody, I'd like to introduce you to my two lab assistants, Noni and Hlanga.
Hello.
They're from Judea High School. They'll be helping me with my experiments I'll be conducting for the rest of the series. Okay, let's get started. Have a look at my materials I'll be testing. I have some nichrome wire and some copper wire. Notice the length and thickness of these two pieces of wire is the same. Now, we're going to conduct a similar experiment to the one that Ohm did. In this way, we'll be able to see if there's any differences in the way that these two metals conduct electricity. I'd like you guys to test the nichrome first, and then test the copper wire. Here's some practical investigation sheets, and I'd like you guys to read the instructions carefully before you start. And I'd also like to check if the apparatus is connected correctly before you guys take your readings.
First, we need to set up a circuit. This circuit diagram looks easy enough to follow. We have the power supply connected in series to the rheostat. I'll connect the positive end of the battery to the end of the rheostat.
Next, we have to connect the rheostat to the wire. Now we have to connect the wire to the ammeter.
Remember to put this connecting lead into the red positive terminal of the ammeter because we started from the positive terminal of the battery. Conventional current direction is from the positive terminal to the negative terminal.
Good thinking.
Next is the switch.
Now we need to connect the voltmeter in parallel across the wire.
The red terminal needs to be connected to the end of the wire next to the rheostat, and the black terminal must be connected to the end closest to the negative terminal of the battery.
Okay, I think we've got it. Excuse me, sir. Can you please come check our circuit?
That all looks right. I'm glad to see that you have both the meters connected correctly. If you don't remember to follow the directions of your current from positive to negative, you might destroy them. Now let's check your rheostat settings. Now you'll control the amount of current flowing through your circuit with your rheostat. Because we want to compare the readings on the meters as the current increases, we're going to need to have a small current to start with. So the rheostat needs to be set in a way that the current goes through more loops. By moving the top adjuster, you'll be able to decrease the number of loops and increase the current. I think you're ready to start taking the readings. Now remember to follow the methods given on your instruction sheets carefully. To get accurate results on this experiment, you will need to close the circuit, take your readings quickly, and then open the circuit again. Now this will ensure that the temperature of the conductor remains constant.
I'll record the readings in the table on the instruction sheet.
Sure, but let's both take the readings. You take the readings of the ammeter, and I'll take the readings of the voltmeter.
Yeah, okay.
I'm going to close the switch now.
The readings on the ammeter is 0.2 milliamperes.
And the reading on the voltmeter is 0.8 volts.
Quickly open the switch.
Okay. The instruction says that we have to let the wire cool down for a few minutes.
I think that's long enough.
Okay. I'm increasing the current.
Okay, the reading is 0.4 milliamperes.
And the reading on the voltmeter is 1.6 volts.
Turn the current off.
Okay. I've increased the current again.
Right, now we have to do the exact same process, but with the copper wire connected in the circuit.
Okay.
0.4,
Okay.
0.8,
Okay.
1.2,
Sorry.
and 1.6.
Right. There we go.
Now I think the learners are finished taking their readings and are now plotting graphs on potential differences in current. Take a careful look at the results they have obtained. Can you plot a graph of these results? Use a graph to compare the resistance of the copper and the nichrome wire. Let's have a look at the graphs the learners drew.
For the nichrome wire, we found that the potential difference is directly proportional to the current, since we were able to draw a straight line graph passing through the origin. We also measured the gradient of the line and found that the resistance of this nichrome wire is 4 ohms.
For the copper wire, we also got a straight line, but the resistance of the copper wire was 2 ohms.
So even though the wires were the same length and the same thickness, and we tested them the same way, we got a difference in measures of resistance. This must be because the nichrome and the copper wire are made up of different types of atoms. So why don't we go to studio and see if Diasha's got any answers.
Well, Tate and the learners certainly got some interesting results. Let's have a look at a model of what happens at a microscopic level to see if we can explain the differences they observed. In all metal atoms, electrons are arranged in energy levels around the nucleus. The energy levels close to the nucleus contain electrons, but there are many high energy levels that remain empty. The last energy level that contains any electrons is called the valence energy level, because it contains the loosely held valence or outer electrons. When metal atoms combine together in a metallic lattice, the valence energy levels of each atom overlap and combine to form a band of energy levels called the valence band. Electrons in a metal lattice can drift from one atom to the next in the valence band. In the same way as the valence band forms, unfilled energy levels also combine to form high energy bands. The energy band closest to the valence band is called the conduction band. In most metals, the valence band overlaps the conduction band. So, when electrons in the valence band are supplied with a small amount of energy from a battery, they can move freely in the conduction band. However, the size of the overlap is not the same for all metals. When the overlap is large, the resistance of the conductor will be small. When the overlap is small, the resistance is larger because more energy is required by the electrons to get into the conduction band. And that's why we found that the resistance of the nichrome and copper wire were different. The overlap is smaller for the nichrome wire, which had the larger resistance. The overlap for the copper wire was larger, which had the smaller resistance. This means that different metals or combinations of metals can be used to make resistors of different ohmic values. The resistance of each of these resistors will remain constant for all values of current and potential difference, as long as the temperature doesn't change too much. Now, there's one very useful resistor that isn't usually used in electronic circuits: a light bulb. Inside the glass of a light bulb, you can see a thin coiled piece of wire called a filament. This wire glows with different brightness when a current passes through it. As you know, when you use a light bulb, it releases lots of energy in the form of heat and light. So the temperature doesn't stay constant. What effect do you think will that have on the resistance of the light bulb? Well, this is exactly what I want you to think about for your task today. I asked the learners that helped out in the lab to set up an experiment to test the resistance of a light bulb. I want you to analyze the results the learners got when using a light bulb instead of the wire. Use this table of results to draw a graph of potential difference and current for the light bulb. Use your graph to draw conclusions about the way a light bulb filament conducts electricity. Explain your conclusion in terms of energy band theory. Well, I hope you enjoyed finding out more about resistors in this lesson. Resistors play a very important role in electronic circuits, as they can be used to control the size of the current passing through other components in the circuit. In our next lesson, we'll look at what happens to insulators when a potential difference is applied to them and see how we can use these materials as useful electronic components. See you then.